Okay, kids, we're back, and we moved on to motion of charged particles in an electric field. Motion of charged particles in an electric field. So let's do this first example here. And what we have here is this positively charged particle, and we're going to call this positively charged particle having a number of coulombs of charge Q2. And over here is another charged particle, and it's positive, and it's got a charge Q1, so many coulombs Q1. Now this charged particle here, this big one, is fixed. It can't move. And originally, the distance between them, center to center distance, is R initial. There it is. This particle is free to move. And let's say momentarily it's being held there by whatever force, okay? And then if it's being held there, it has an initial velocity of 0. Then that force is removed, and this charge Q1 is free to move. And here would be a free body diagram on it, right there. So it's being held temporarily, then boom, maybe a little gate is open, and boom, off it moves because now there's an electric force on it. And remember what the magnitude of this electric force is. It's equal to K, Q1, Q2, all over how far apart they are, center to center squared. That's the situation there. Well, let's try to look at this. As it's moving, we can say, well, what's the net force on this mass for Q1? So let's say, what's the net force on mass 1? Well, it's equal to mass 1 times the acceleration it's undergoing. Well, the only force acting on it is the electric force right there. So we can put that in. So that'll equal m1 times the acceleration. Well, what's the acceleration equal to? Well, the acceleration is equal to the force electric, that's the only force acting on it, divided by m1. So if we want to study the motion of Q1 as it is accelerated away from Q2, if we want to study that motion, take a look at this. It's saying that the acceleration is equal to force electric divided by mass. But force electric depends on how far away the two charged particles are from each other. It's actually a 1 over r squared relationship. So that means that the acceleration is proportional to, or is dependent upon, 1 over r squared, how far apart the charged particles are, right? R squared, it's 1 over r squared. So that means that the acceleration is not constant. It changes. As the particles get further and further away from each other, the force electric gets weaker and weaker and weaker. The force electric gets weaker and weaker and weaker, and that means the acceleration gets smaller and smaller and smaller. It's still being accelerated, but the rate of acceleration is smaller. It still is speeding up as it moves away. It's just that rate of speeding up has been decreased. We don't usually deal with accelerations that are not constant. We don't really have a lot of the math that would allow us to use this. One day you will. It's called calculus, or as me and my buddies used to call it, calculost. All right? We don't have that yet. So since the net force is equal to the electric force and it is proportional to 1 over r squared, because of these two consequences right here, and they are the same consequence, it's best to use another way of solving this. It's best to use my friend and yours, the work and energy method way of looking at this. And that's what we're going to do. So here we are back again. We're going to, as I said, we're going to use the work and energy method way of doing this. So here's the situation. The charged particle Q1 has moved. Remember, Q2 does not move, it's fixed. And now it's at a new centered distance called RF. And what we want to figure out is when it's at this new distance, how fast is it moving? All right, so the way to approach this, as we said a few moments ago, is to use energy methods. So we say that the energy total initial is equal to the energy total final. We're going to use this. And energy total initial was kinetic energy initial plus electric potential energy initial. We've got these two terms on the left-hand side. On the right-hand side, we have energy kinetic final plus energy electric potential final. Here we have the two terms. Now, next, the initial kinetic energy is zero. It was not moving. So now we're going to put in the equations for electric potential energy. There it is. I put in the equation for it equals electric potential energy final. I put in the equation for it. And kinetic energy final. I put in the equation for it right there. Okay, so take a moment. If you have to pause the video, that's an ugly F. There we go. And go from this line here to the next one. Okay, figure that out. If you have to pause the video, pause it. Now, a couple of things to remember about electric potential energy. Electric potential energy is dependent on how far the charged particles are from each other and it comes in two forms. One where there's attraction and the electric potential energy would be negative, and one where there's repulsion and the electric potential energy would always be a positive quantity. In this particular situation, it's repulsion. So electric potential energy would be positive. Let's continue. What we're going to do here is we're going to bring this term here over to the other side, and it becomes negative. If I take this term over to the other side, it's negative, and I'm going to factor out a k, q1, q2 out of these two terms. I'm factoring out a k, q1, q2 out of these two terms once this term has been brought from the right side to the left side of the equation and therefore made negative. And this is the expression that we have. If you have to pause the video to rationalize that in your mind, please do so. And on this side here, we still have the kinetic energy expression. So now what we're going to do is we're going to multiply both sides by 2. It'll clear out the half, and I get a 2 out front. I'm going to divide both sides by the mass, so it clears out the mass, and I got a mass in the denominator here. And lo and behold, I have found a way to find the final speed of the object by using energy methods, which is the only way we can do it at our stage of mathematical ability. Okay? Now, the thing you have to realize, and it's really at the heart of why we had to use energy methods, is the electric field here in this area here is caused by the electric field from charged particle Q2 plus the electric field from charged particle Q1. And this field varies. It's not constant. No way. What's the equation for electric field? K, Q, all over R squared. Look, it depends on how far away you are from the charged particles. This varying electric field leads to the varying force, which leads to the varying acceleration, and which leads us, once again, to having to use energy methods. Very important to remember that. The next main area of study here is the motion of a charged particle when the electric field is constant. All right, now we're moving to a different situation. All right, now we have dealt with motion when we have had constant fields. Here's our friend G. What's up, G, I haven't seen you in a while. We've been doing all this electricity stuff. Finally, you're back, G. Yes, and G is going to help us understand this. In grade 11, we did questions like a ball is dropped straight down in a constant gravitational field, or thrown straight down, I should say, in a constant gravitational field. A ball is thrown straight upward in a constant gravitational field. Or a ball is dropped, right? Initial velocity 0. Straight down it falls in a constant gravitational field. Then in grade 12, we moved to something slightly different. We added another dimension, 2 dimensions. Now a ball may be shot completely horizontally in a constant gravitational field. Or a ball is thrown forward and upward at a constant in a constant gravitational field. Or maybe it's thrown forward and downward or backwards and downward in a constant gravitational field. And these three right here all led to my friend and yours projectile motion. That's what it led to. Projectile motion. It was really cool. We want to see if we can understand the motion of a charged particle in a constant electric field, and so many of the things that we learned about motion in a gravitational field, a constant gravitational field, will help us with that. I hope you're ready. I'm excited. Are you? So here's an example. Let's say we've got this set up. Remember, we need 2 dimensions now, y hat and x hat. And let's say that this object, an electron, is shot forward so that the y component of its velocity is 0, but there is some x component to it. I just don't know what it is right now. It doesn't matter. So it's shot through like this, and the motion, kids, as it's shot through like this, will be a parabola. That means that we can now apply all that we know about electricity and voltage and electric fields and all that fun stuff, and we can combine that with what we learned very early in this course, because now this means we can do projectile motion again, but not with gravitational fields, with electric fields. This is awesome. I think we should do some examples to really help us understand all of this. Agreed? What was that I heard? Agreed. Awesome. All right. Our first example. Our first example here. Here are two charge plates. Negative plate, positive plate. And right here, I've got an electron. And somehow, this electron, we know the charge on it, we know the mass on it, somehow it's being held there. Maybe the Scarlet Witch has put some hex on it and it's not moving. Somehow, it's not really important, but at this point right here, it has an initial speed of 0 meters per second. And then we're going to let it go. We're going to release it somehow, and off it's going to go across because it's being repelled by the negative plate and attracted by the positive plate. So it's just in contact with the negative plate. It flies away and it's going to impact the positive plate. And when it impacts the positive plate, we want to know what its speed is. This is not that different than when we were in grade 11 together and I held a ball and a ball fell through a gravitational field. Now, an electron is, listen to the word I'm going to use, an electron is falling through an electric field. So when it hits this plate here, everybody knows that the final speed will not be 0. It's going to impact the plate. So what else we know about this situation here? Well, we know that these plates have an electric field in here and that it is constant. There's a constant electric field in here. That's why I can say to you, this is very similar to a ball being dropped through our friend G, negative 9.8 newtons per kilogram, constant gravitational field. And that electric field that is present here can also be described by saying there is a voltage difference between these plates of 2.0 times 10 to the 4 volts. So now, before we have to answer this question, or are going to answer this question, we really need to investigate what voltage difference actually means between these two plates. So this is what we're going to do right now. We're going to investigate this, get a greater understanding of this before we move on to solving this problem. So I'm going to redraw this. So once again, here's my positive plate and here's my negative plate, and I want to investigate voltage. Anytime you want to investigate the characteristics of an electric field or a potential difference, the situation brings up that you have to use a positive test charge. Everything is defined by a positive test charge. Even though I eventually am going to answer a question about a negatively charged electron, as all electrons are negatively charged, to get an understanding of the condition of the voltage of the electric field that this electron is experiencing, I need to define that voltage. I need to define that electric field by using, you guessed it, a positive test charge. So let's investigate. So if I have a positive test charge right here, let's say it's actually touching the negatively charged plate, it's got nowhere to go. It's moved as far as it can move. It has no potential to move anywhere else. So that means along here is the lowest electric potential energy that can be established. Along here is your zero electric potential energy. And then as you move away from it, then this positive test charge has the ability to fall through the electric field. So here would be a higher voltage line. And then even further, a higher voltage line. And then even further, a higher equipotential electric voltage line, until you got to the positive test charge actually being at the positive plate. And that's where the positive test charge would have its highest possible electric potential energy. That's where it is the highest, because it has the potential to fall through all of the electric field. So that means here we have a low electric potential energy for a positive test charge, and here we have a high electric potential energy for a positive test charge. Now let's take a look at the definition of voltage. Let's take a look at the definition of voltage. Voltage is equal to electric potential energy divided by charge. So if I have a low electric potential energy and I pop it into this equation, it means that along here I'll have a low voltage. Low voltage here. Actually, right along the negative plate, it would be a zero voltage. And if I put in a high electric potential energy into the equation here, so plug in a high electric potential energy, that means I'll have a high voltage along the positive plate. At the positive plate, you would have absolutely positively the highest possible voltage. Let's continue our discussion here. We haven't even attempted to answer the question yet. Let's pretend I have a situation where there's a voltage difference of 12 volts between a positive plate and a negative plate. And I've drawn the electric field lines. Electric field lines always go from positive to negative, because if we had a positive test charge here, it would feel a force in that same direction. Remember, positive test charge. That's how fields and voltages are defined. Well, I can then start to draw equipotential lines through this field. And I can say that along the negative plate would be a line of 0 voltage. Then maybe a little bit further would be a line of 3 volts. Maybe a little bit further away, a line of 6 volts. A little bit further away, a line of 9 volts. And then finally, I get to the other side, completely to the other side, to the positive plate. and I would have a voltage line of 12 volts. So I've gone from 0 volts to 12 volts. That's why the voltage difference is 12 volts. If you need to stop now and rewind some of what I talked about here to really give you an understanding of voltage in a constant electric field created by two parallel plates, do so now, because what I'm going to move to now is actually solving the problem now that we've delved deeper into this constant electric field phenomenon. All right, so I think we are ready to solve this problem where you had an electron here, negatively charged, with a known mass being held temporarily, initial speed 0, and it flies into the positive plate, and we want to find the velocity. What we're going to use here to solve this, and there would be other ways to solve it, but what we're going to use here in this situation is law of conservation of energy. So that the total energy initial is equal to the total energy final. I forgot my F. Total energy initial is equal to the electric potential energy that the object has there, plus its kinetic energy there. It wasn't moving here. Zero kinetic energy. And on the other side, total energy final is equal to the electric potential energy final that the object has when it gets to the other plate. So what is its electric potential energy when it just touches the other plate? That's the term right here. And what is its kinetic energy when it gets to right there? So you have to remember the relationship between electric potential energy and voltage. I wrote it for you right there. See it? So if you rearrange this equation, you get electric potential energy is equal to voltage times the Q that would come up. So that's why I'm changing electric potential energy to the charge that the object is carrying times whatever voltage conditions are present in the initial situation. And that's going to equal electric potential energy final, which is now the charge that's being carried by that object multiplied by whatever voltage conditions exist in the final situation, plus half mvf squared. We've done that for years now. What I'm going to do is I'm going to take this term, QV voltage final, Q voltage final, and this is a big V, okay, and bring it over to here. And I get Q big V I minus Q big VF is equal to half M little f, excuse me, little v f squared. So please, it's kind of confusing. V for speed, V for voltage. It's big V for voltage, little v for speed. I hope that's okay. Now what I'm going to do is I'm going to isolate for the final speed squared. So I multiply both sides by 2. There it is. Divide both sides by m. There it is. And I've also factored out a q out of both of these terms. Factored out a q. If you have to pause the video now to see how I went from this line to this line, do it. Try it yourself. Okay, it's always best when you try it yourself. I did some factoring and I did some isolating for the variable. And I plug in the numbers into the equation right there, all known quantities. It's a square root situation, and I use my handy dandy fancy dancy calculator, and I get the final speed. There you have it. Okay? So I hope this example showed you how to solve one of these problems, but I also hope it gave you a deeper understanding of the relationship between voltage and electric field between two parallel plates where the electric field is constant. All right, so here's another example, and this is a projectile motion question. Here is two charged parallel plates. There's the positive plate, there's a negative plate. These green lines here are the constant electric field that's straight downward. All right, very similar to a constant gravitational field, our friend G. All right, now what we have here is this little red dot here is an electron. That's the electron right there. And the electron is shot horizontally into this constant electric field. That means its initial y velocity is 0, and it's shot, and it will go through a parabolic path till it gets to here, just leaving the parallel plates. It's a parabola. We're talking about projectile motion here. And we want to know, what is its final velocity right there? What is the final velocity right there? What do we know? Well, we know that the plate has a certain length, 0.05 meters, and that is all in the x direction, this length of the plate. And we know that there's an electric field, and the electric field is negative 130 newtons per coulomb y hat. So this is the electric version of our G, negative 9.8 meters per second squared, or negative 9.8 newtons per kilogram. But now it's electric, okay? Let's continue then. We know also that this initial velocity is positive 2.5 times 10 to the 6 meters per second, all x hat. And we want to find the final velocity. So let's continue. Final velocity is equal to final velocity x component and the final velocity y component. But I hope you remember from projectile motion that the x component of the velocity doesn't change. And that makes a lot of sense because the electric field is straight down. So electric force is going to be created that is also straight down. Just like when we have force of gravity on an object near the surface of the Earth, the gravitational field is straight down, so the force of gravity will be straight down, which led to an acceleration which was straight down. The same thing's going to happen here. The electric field is straight down, therefore the electric force on that charged particle will be straight down, all negative y, and the acceleration that it experiences will all be in the y direction, straight down, no acceleration in the x direction. The x velocity does not change. So we need an equation to find final velocity y component. Well, final velocity y component is equal to initial velocity y component plus the acceleration in the y direction multiplied by how much time the object was experiencing that acceleration. Well, we don't know these two. Don't know them. We need to figure them out. How will we do that? Very similar. It is a projectile motion question. Let's find delta t. We can use this equation right here. Velocity in the x direction is equal to displacement x component divided by time. We rearrange it. And now time can be calculated because we know how long the plates are, right? And we know how fast it's moving in that x direction. So it's going to take a very short amount of time, 3.0 times 10 to the negative 8 seconds. That's how much time it is in the area between the volume between the two parallel plates. So bingo, I figured out t, time. That's great. Very, very similar to how we've done it in the past for gravitational fields. Next, we have to find acceleration in the y direction. Well, let's use the most important equation in physics, F net equals ma. F net y direction is equal to m times acceleration y. Well, the net force in the y direction is all electric force, all of it. All of it is electric force. And it is equal to the mass of this electron times its acceleration in the y direction. Electric force, if you remember, is equal to charge times the electric field. That's what electric force is equal to, which would equal mass times acceleration in the y direction. We isolate for acceleration in the y direction by bringing m down, the mass down underneath, and we now are going to plug in the numbers. There we have it. Electric field, negative. Electric charge on the electron, negative. The mass is always positive. And we get an acceleration which is positive. 2.3 times 10 to the 13 meters per second squared y hat, which makes a lot of sense. This makes a lot of sense because it's a negatively charged particle, so it's going to feel a force upward or a force downward. Okay, so here we go. Upward. Should have said that. All right. Positive acceleration. So now we know both values. We plug it in and we find the final velocity y component. And we're done this example. I know today was a long lesson. Thanks for hanging in there. Really appreciate all of your efforts. Have a great day. Bye-bye.